So let's start with the presentation, and I'm going to present hardware acceleration of homomorphic encryption. Let's start with what homomorphic encryption is. Basically, homomorphic encryption is conversion of data into ciphertext, which can be analyzed and work with as if it was still in its original form. Here we can see that we can perform functions on the plain text as well as on the encrypted messages. So if a third party is performing these functions, they'll not be able to get the plain text MA. They can continue to work with the encrypted message, and later we can decrypt the result f of m and get the original plain text message. So this homomorphic encryption enables complex mathematical operations to be performed on encrypted data without compromising the encryption. And here, basically, the homomorphic describes the transmission of data from one set to another while preserving the relationship between both the elements in both the sets. And here we can see this has a lot of applications, and you can see and it enables mathematical computations to perform directly on the encrypted data, and it also make handling of user data by third parties safer, as I already said. And here we'll use a cryptographic key basically to encrypt and decrypt the message. Now let's see what number theoretic transform is and how it is used in homomorphic encryption. Basically, what we do here is that in homomorphic encryption, we involve a polynomial multiplication, and here ciphertexts generally are very long, and the polynomial multiplication will take a lot of computational resources and time. So instead, what we are going to do is we are going to perform entity on the ciphertext. So we get the entity output, and upon getting this output, we can directly perform element-wise multiplication and later do inverse entity and get the output ciphertext. So here we are replacing normal multiplication with element-wise multiplication. This will save us computational time and resources. Now, there is a need for accelerating entity, and let's see that. If you take two of a commonly used encryption methods, Microsoft Seal and IEEE HPCA 19, you can see significant amount of the computation time is consumed by entity and INTT processors only. Here, entity and INTT are performed in software. So basically, what we are going to do is we are going to perform this in hardware and show that in few cases hardware acceleration is happening, and we can use the hardware IP instead in place of the software. The main difference of FFT and NTT algorithm is that the first operates over reals, while the second operates over a final field. And also here in NTT we use modulo multiplications, unlike DFT's floating point multiplication. Here, if you see normal multiplication will be O of n square, but here the complexity after performing entity, we since we do element-based multiplication, it's O of n log n. So here we are saying a lot of computational time and resources as well. Now let's go and see the implementation of entity. This is just an entity IP project. Here we are going to make the IP which will perform whichever entity form we want. The form in the sense here what we are going to perform is we are going to perform 8 input entity. We'll give 8 inputs and get 8 outputs, and width of each input is 4 bits. So basically this is the code here. uh, let's first see what entity is in a formula way. Entity is basically forward transform entity is basically this transformation, and here we do modulo operation with the prime number which will all give it as input. So this is basically entity, and inverse entity is basically a change in sign here. And as we can see here, and it's obvious, inverse of entity performed on entity output will give the same input, and this is what I explained before. Say we have two inputs f and g. Those are two polynomials. Instead of doing normal polynomial multiplication, we are performing NTT on them, and then we are directly doing element-based multiplication. After performing it, we are taking inverse of it, and we'll get the output here. So this is what we are basically going to do, and we have performed the same thing in Verilog here. And since Verilog doesn't support packed arrays, I have unpacked the input and again taking it as an array here, because it's easier to work with Verilog vectors. And again here, after performing this particular logic and doing mod q everywhere, I'm again giving each and every input to the output. So this is just implementing this particular thing for every I, and there is a recursive j for every element in the each input. So now let's pack an IP. Let's go to tools and create and package an IP. in our project we are going to use HC4 protocols, and let us give it as my IP only. My Here we are going to use HC4 Lite protocol, and HC4 Lite protocol we are going to use only one interface, and each interface has 32 bits wide. Basically here we are having 8 inputs. Each input is 4-bit wide, and also 8 output. So we can put all the inputs in one particular register, and register can be used for outputs. Third register can be used for the prime modulus and the twiddle factor. So but here since we need to use minimum of 4 registers, we'll keep it as 4, and then we'll give edit IP and finish. Since we give edit IP, we'll get a new window now. This is the code for my IP, and this has used HC Lite protocol here. Let's incorporate our own entity code into this. So first what we'll do is we'll copy this code, and in this edit window we'll just add design source, create a file, give model name as entity, and paste this code. So now basically we have an entity file here with model name entity. Now let's go to the Verilog file here, and here basically these 4 are the registers. These registers are the ones we can access, and these follow HC4 Lite protocol. And what we are going to do is we are going to give input in one and take output in one, and the next register is for twiddle factor and the prime modulus. Let's go to the declaration part and declare a wire of 32-bit wide and name it as out. In place of SLV reg3, we'll give that out. Now here we have to add our own code. Since we gave edit IP, we can edit it with our own code. I'm going to call my entity module from here. In entity module, we'll have to give 8 inputs. 8 will get 8 outputs, and these two are also inputs here, the twiddle factor and the input. So we'll just write it here. So this is the variable names in the original IP. Now we are going to make connections with our own IP here. First we'll call SLV red 0, and width of SLV red 0 is 32 bits, but we only want 4 bits, so we are going to slice it. Here we are going to use the next registers, and we can see here that the prime modulus is 8 bits wide. So we'll use 8 bits here, and the twiddle factor is 5 bits wide. We can change it to 4 bits here so that everything is even. It doesn't matter anyway because and twiddle factor won't be that big anyway. So this is not going to affect the code now. And for NTT out, we are going to do the same thing, but here we are going to get it from our own register which we declared or via here. We don't have any error over here, and we are basically connected this particular registers to our particular design. Let's save the file. Now since we have made changes, and we can see since we have called entity, it is given under this thing. Now we'll go to this file, and since we have made changes, we'll go to file groups and we're going to merge all the files we have added. Now we'll repack this IP, and this packed IP will be found in the particular repository. If you go to IP repo, we can find my IP1 here. This is the IP which we made now. I have made IP for every other thing as well. Here we can see we have 32 inputs and each input is 8 bit wide. I'll open one thing for example. Let's open 128 bit. So this is basically file for that particular thing, and we can see here I have given 16 out declared 16 outputs because we are going to give 128 input and take 128 outputs. Each is 32 bit wide, so in each thing we'll have 8 numbers. So first 8 numbers are in output 1 register, next 8 are in output 2. In that way we have 128 inputs and 128 outputs. So here we can see instead of the original outputs we have changed it to output 1 to output 16, and here we are giving the input, and here also we are going to slice it, and this is how we are giving the inputs. So this way we are going to connect our entity module to this particular file. This is for 128 inputs, each input is 4 bit wide. Now let's see for what happens if it is 8 bit wide. We'll go to 32.8 IP. In this also we are going to have, since it is 32 inputs and each input is 8 bit wide, in one register we'll have 4 outputs and 4 inputs. So we'll need to have 8. Here also we are going to have 8 register 8 wires we are going to give here, and for output we'll take them, and input we are giving using 8 registers. So this is basically how we make our own IP, and we'll have to change the code accordingly as well, because if we go to this particular 32 IP and we go to the Verilog file that was used here, you can see the Verilog code is changed as well. There are 32 inputs and each input has 8 bit width. Again 32 outputs and each output has 8 bit width. So this is how we basically do it.